So have you been studying a long time, asking yourself what you've overlooked and what easy points you've left on the table? For many people, the answer is combinatorics, or counting problems. Tons of GMAT preppers avoid this topic so much that they don't even learn the basic difference between permutations and combinations, even well into their studying process. But with only 21 questions on the quant section, every question is crucial, and you may be leaving easy points on the table by not equipping yourself to handle combinatorics problems, which are often quite simple if you know the basics. Just getting one or two more questions correct will make a drastic difference for your score. These problems can be intimidating to the point where test prep companies often don't even try to teach them, but they are, for the most part, really quite involve only basic multiplication or other skills you've already mastered. After this video, you'll understand the two major strategies for solving combinatorics problems, and you'll be able to figure out most combinatorics problems that you're likely to encounter on the GMAT. Hi everyone, I'm Dan, otherwise known as Dan the GMAT Man. I do tailored, custom, one-on-one GMAT and GRE tutoring, and I'm also an expert on GMAT Club. So I'm going to be teaching you about combinatorics today. So let's jump in and learn how to count outcomes using the fundamental counting principle. So the most basic element of counting is just the fundamental counting principle. This principle states that if you multiply how many options you have at each pick, at opportunity selection, etc., that gives you the total number of outcomes. So basically you multiply how many options you have for each thing when things combine to make a complete outcome. So how many outfits can I make if I have 3 pants and 4 shirts? The shirts and the pants represent those opportunities to pick things. If I have 3 pants, 4 shirts, 3 times 4 gives me how many total outfits I can make. Okay. So when I was in 5th grade and I didn't pay attention to the teacher, when she explained how to do these, I would just kind of draw them out. You start from the first thing, the first shirt, and you draw little lines to 4 different pants. And then the second shirt, draw little lines to 4 different pants. That's how I would count how many outfits I can make. Well, if you do that on your paper, you look at what's going on, you realize it's just like 3 times 4. You're just drawing 4 lines 3 times. 3 times 4. If I threw in another thing, like you have 2 hats to choose from, then from every pant, I go shirts, then pants, and then I'm just drawing 2 more lines for each hat. I'm doing 3 times 4 times 2. Quick way to do it is just multiply how many options you have for your pants, for your shirts, for your hats, whatever. Those just get multiplied together. That tells you how many total combinations or outcomes you have for outfits. Now, the thing you may be asking yourself, because this is the one kind of idea that people who have studied a little bit will emerge with from doing combinatorics is, does the order matter there? That's what we hear. Does the order matter? Does the order not matter? Did the order matter for the shirts and the pants? Well, I mean, it didn't seem to. We didn't worry about picking pants and shirts or anything like that. So what's kind of going on there? Let's look a little deeper. And the way we organize this process mathematically on our paper is we do slots. You do a slot for every opportunity. So you do a slot for pants, a slot for shirts, a slot for hats. Then you just fill in each slot how many options there are, multiply across. That's it. Suppose you're asked, how many 3-digit numbers can you make using the digits 1, 2, 3, 4, and 5 without repeating digits? So let's use our slot method again. Okay, we have 3 digits, so we're doing 3 slots. Okay, how many choices do you have for the first slot? Well, you had 5 numbers there, so 5 choices. Then, we have to take one out. We can't reuse the same digit, so we take one out. We have 4 possibilities for the second digit. We take another number out, 3 possibilities for the third digit. And that gives you 5 times 4 times 3 equals 60 possible numbers. Notice something important here. The order of the digits matters. Okay, 123 is different from 132, is different from 213, is different from 231. Even if I take the same 3 digits and I reorder them in different ways, all of those count. So that's really what matters, is do the orders count or not? When the orders count, when all the different orders count, that's a permutation. Okay, and even if repetitions are allowed, so doesn't change the problem a whole lot. When you do 3 slots, we'll have 5 options, and then we don't have to take anything out, so 5 options again and 5 options again, giving you 125 outcomes. And so this is, doing things like this will allow you to solve most permutation problems, most permutation situations. Now let's look at a different scenario. So this is going to start to change things up a little bit. What if I am making a pizza? And let's say I have 5 toppings to choose from, and you get to choose 3 on your pizza. So we're using the same numbers we did as before when we made the 3-digit number, but now it's like we're making a pizza and we have 5 toppings to choose from, and you choose 3 on your pizza. Um, Before I said 123 is different from 213 is different from 321. Ask yourself now, is pepperoni mushroom tomato different from pepperoni tomato mushroom, different from mushroom pepperoni tomato? No. Those are all the same pizza. So they're trying to rip you off if they try to list those as different pizzas. That's all the same pizza. You cannot tell the difference between those pizzas. If you say the same three things in a different order, it's not different. You couldn't tell the difference. You can only tell the difference when you swap out one term completely for another. So pepperoni mushroom tomato is one kind of pizza, and then pepperoni mushroom sausage. That's actually a new pizza because we have a new thing being selected. Okay, so this is a combination. Different from a permutation, this is a combination. Notice the order doesn't matter. And that's what people say, but really the way I like to think about it is I don't count different orderings of the same things. Pepperoni mushroom tomato, tomato pepperoni mushroom, no, that's not any different. So that makes it a combination. Whereas before, 213, 321, 312, those are different numbers. That's a permutation. Okay, so combinations here. When you say the same few things in a different order, ask yourself, does that count also? Is that different? If yes, it's a permutation. If no, it's a combination. So how to solve this pizza problem? Well, I can't just do 5 times 4 times 3 like I did with when I made the 3-digit number, because that would be counting pepperoni, mushroom, tomato, mushroom, etc. Here you have to use a formula. You may have seen this, you may have not. The formula is n factorial over k factorial times n minus k factorial. So n is the total number of things you have to choose from, and k is the number you're choosing, or what size groups you're making. Usually this number is stated explicitly like it is here, like we have 5 toppings to choose from and we're choosing 3. N is 5, k is 3. There may be some problems where it's confusing. It's not stated explicitly what your k value is, but you always think to yourself, well, what size groups am I selecting? That's your k value. So here's 5 factorial over 3 factorial times 2 factorial, and I'm going to show you how to simplify here. You just kind of cancel the largest factorial out of numerator and denominator, and you continue to cancel terms until your whole denominator is cleared out. Solve for it. That's your answer. So to recap on the difference between a permutation and combination, there's one test you can do that works every single time. You just say the same 3 or 4 or whatever things in a different order and ask whether that also counts or whether that's distinct. If yes, it's a permutation. If no, it's a combination. So how many friends can I take camping? Joe, Jeff, and Mary. Mary, Jeff, and Joe. That's the same group of people. It's not distinct. That's a combination. Whereas when I'm making numbers, again, 142, 241, yes, those are different numbers. That's a permutation. I'm using slots always for permutations. I'm using the formula always for combinations. Okay. Something to remember, most permutations problems are doing spatial arrangements, making numbers, arranging people in a line, physical arrangements, or making numbers like we did before with, 3-digit numbers using so many different numbers. Most combinations are making groups, teams, committees, or drawing geometric shapes within other geometric shapes, like how many triangles can you draw between 8 points. Notice like point ABF, point FBA, that's the same triangle. That's a combination. It's not distinct if I say the points in a different order. So now let's look at a couple of different scenarios. When we selected pants and shirts and hats, those were clearly different items. They're coming from different buckets. So you have your pants and you have your shirts, and these things cannot be confused with one another. They're not coming from the same bucket. You clearly have different buckets of pants, shirts, hats. But what if let's say I'm packing for a trip and I want to take 2 shirts instead of just 1? It gets a little bit more complicated. We can try to draw the slots for pants and shirts, but your pants and hats are pretty clear. But what about the shirts? Is that just like 2 slots and you fill in your numbers? Let's see. Can I do 3 times 2 for the number of shirts I can take? Like 3 options for the first shirt and then 2 options for the next shirt? Well, does the order matter? I'm doing permutations because order matters usually. But if I take my blue shirt, my red shirt, and my red shirt, my blue shirt, is that a different selection? No. Okay, it's the same selection. So I have to treat this part of it like a combination. Drawing the shirts is like a combination. It doesn't matter whether I take shirt A and B and A, no, it's the same selection. Okay, so I'm going to do a combination for, I have three shirts to choose from, and I'm choosing two. My N is 3, my K is 2. Once I get a value for this, then we're back to the fundamental counting principle. Okay, I've gotten a value for how many unique selections of shirts I can make, how many unique selections of 2 shirts out of 3 I can make. So I have a value now for the number of shirt selections that are possible. So it's back to just multiplying my options. The number of pants times that value I just got for the number of unique selections of shirts times the number of hats. Okay. What's tricky here is that sometimes selections are being made from the same pool or from different pools. That's where you have to watch out. Let's look at 2 examples. So how many ways can 10 employees all shake hands with each other if each employee shakes hands with every employee just once? So it's just how many handshakes are there going to be? Or a different question is, suppose there are 10 directors in a company and 10 managers. How many handshakes are exchanged if each manager shakes hands with each director, but no directors or managers shake hands with each other? So you have just a director shakes hands with a manager, but the directors don't shake hands with each other, the managers don't shake hands with each other. Just how many handshakes are exchanged if every director has to shake hands with every manager? What's going on here? There's a little difference. Let's look at what's going on. So in both cases, it takes 2 people to perform a handshake. So like if you're doing a combination, this is what I mean by like think what size groups you're making groups of 2, because that's how many people it takes to do a handshake. In the first example, 2 people are being chosen from the same pool. You just have 10 people with 10 employees with no distinctions in between them. So you have 10, you're using your combination formula, because we don't, like Bob shaking hands with Steve is not different from Steve shaking hands with Bob. So we just have 10 people to choose from, and we're choosing 2. Now in the second example, you're choosing 1 person from each of 2 different pools. So in the first example, I don't want to count Mary and Bob, but also Bob and Mary. This is just a combination 10 choose 2. N is 10, your K is 2. In the second example, notice I don't run into that problem of Bob and Mary or Mary and Bob, because I'm selecting from different pools each time. So I won't accidentally get Mary, Bob, and Mary, because I can only pick 1 person from this pool, 1 person from this pool. And never mind if there happen to be 2 people with those names, they're different people. The point is I won't accidentally select the same 2 people in a different order, because I'm picking 1 from each pool. They're coming from different pools. So I don't have this issue. So this is really just the fundamental counting principle. I have 10 options for the director and then 10 options for the manager. 10 times 10. This, this is just the fundamental counting principle. Multiply how many options you have at each pick, like pants and shirts. Okay. The first example, it's like the employees are like all shirts. So it's like when I did 3 choose 2 to do the choose shirts. Because shirt A and B is not different from B and A. Same thing with the employees. It's like they're all shirts. I'm choosing 2 out of those 10. But when I'm talking about picking a manager and picking a director, I have a pant and a shirt multiplied together. Now to sort out the confusion there, strictly speaking, everything there is a combination, is a selection. It's just that when I selected the managers, select a manager, it's a 10 choose 1. Which, if you do the math in your paper, you see just equals 10. And when I select a director, it's a 10 choose 1. If you do the math in your paper, you see that just equals 10. Anytime you choose 1 out of something, your number of possibilities is that something. So when I did the pants and the shirts and everything like that, strictly speaking, it was a 3 choose 1 for 1 pant, 4 choose 1 for 1 shirt, 2 choose 1 for a hat. So notice they are selections, but it's as simple as just multiplying how many options you have, because you're only selecting 1 of each. Okay, but it's ultimately the same thing. You could look at different examples with possible values of x, y. So in one case, x and y are in different sets. In another case, x and y are 2 different numbers chosen from the same set. Okay, so in the first one, what is it? X and y are chosen from different sets. How many possibilities are there for the value of x, y? But just how many possibilities of x there are times how many possibilities of y there are. Notice, strictly speaking, it's like something choose 1 for x, something choose 1 for y, but then those just get multiplied together. In the second case, they say x and y are just 2 different numbers choosing from the same set. I have the possibility of redundant outcomes, picking this number and that number and that number and this number. So this needs to be a total choose 2 situation. Now, another skill that we need to have is we need to know when we multiply versus when we add outcomes. Um, okay, so the distinction is between and or. Is this an and situation or is this an or situation? You may have heard something like that. Let's clarify what we mean about using and versus or. So in one example, let's say you need to make a committee of 4 people. You have 11 men, 9 women, and you need to make a committee of 4 where there are exactly 2 men and exactly 2 women. Okay. In another example, we're going to make a committee of 2 people, and it can either be 2 men or 2 women. Okay. Let's look at the difference here. In the first case, we need to make 2 men and 2 women. Now, when we choose the men, you'll probably think to yourself, this is a combination. I don't want to count Bob and Steve, Steve and Bob. So I have 11 men to choose from, and I'm choosing 2. I have 9 women to choose from, and I'm choosing 2. I'm going to solve and get those values. Then what do I do with this? Well, it was 2 men and 2 women. And means multiply. You say and, you multiply. When you say or, you add. So in the second situation, notice the difference. We don't want 4 people. We want 2 people. And it can either be 2 men or 2 women. So I do the same combinations to get 11 choose 2 men, 9 choose 2 women. Okay. But what do I do with those values once I get them? It said 2 men or 2 women. I add them. Okay. Commonsensically, it should not be nearly as many outcomes because they're not combining together to create a complete outcome of 4 people, like the way pants and shirts did. Here, it can either be this many groups of men or this many groups of women. You're just kind of like listing them all out, just adding those together. Okay. I like the way a student said at one time. She said, they're happening at the same time. In the first scenario, they're happening at the same time. That's the question you ask yourself. Are they happening at the same time or not? In the first scenario, they're happening at the same time because they're coming together to create a complete outcome of 4 people. 2 men and 2 women combined together to create a complete outcome of 4 people. It's like doing pants and shirts. It's just that you have to first you do the combinations to get how many unique groups of men there are, how many unique groups of women there are. But once you get that, they come together like pants and shirts to create a complete outfit. 2 men, 2 women, those groups come together to create a complete outcome of 4 people. In the second outcome, they're not happening together. It didn't say 4 people, we're going to choose 2 people. And it can either be this, 2 men, or that, 2 women. So they're not happening at the same time. These are completely different scenarios that just get added together. Now, another situation that throws people off is everything we've done so far, all the terms were distinct. So we have Bob, Steve, Mary. There's no like perfectly identical twins or anything like that. But what if we have identical terms? So for example, let's say, how many ways could you rearrange the letters of the word circle? Okay, ask yourself, is this a permutation or a combination? Does the order matter here? If I do the letters in a different order, is that different? Well, yes, because this is the spatial rearrangement. They care about how many different ways we rearrange the letters. So this is fundamentally a permutation. Okay, there's 6 letters there. It just regularly there would be 6 factorial outcomes. It would be 6 times 5 times 4 times 3 times 2 times 1. Just the most basic thing with permutations is that there are n factorial ways to rearrange n different things. So if all 6 letters were different, it would be 6 factorial. But notice the 2 C's are identical. If you imagine these letters rearranging and swapping with each other, if you hold all the other letters in place and have the C's switch with each other, that's not any different. You can't tell the difference when the C's switch with each other. So mistakenly built into that 6 factorial is all these outcomes where, along with everything else happening, the C's are switching with each other, which is never unique. Okay, so we need to divide out the ways that the C's do switch with each other, which is 2 factorial. So for this is a very specific situation where it's fundamentally a permutation, but you have terms that are identical to each other. So usually rearranging letters, it could be identical copies of books or like flags that have no insignia, they're just 4 blue, 3 yellow, something like that. It's going to be n factorial over k1 factorial, k2 factorial, k3 factorial, etc. as necessary. These k1, k2, these are how many groups of identicals there are. So for example, the word Mississippi, how many ways to rearrange this? So you have 11 total letters, 11 factorial. There are 4 I's, so 4 factorial, 4 S's, so 4 factorial, and 2 P's, so another 2 factorial. How did you find this video? Did it clarify combinatorics and make permutations and combinations easier for you? If you enjoyed this content, hit the like button and share this video with your friends who are also prepping for the GMAT. I'd love to hear your thoughts, so leave your questions, comments, or feedback down below. To test your understanding, I've added 5 practice questions on permutations and combinations in the video description. Give them a try, submit your answers in the comments, I'll personally review them. Lastly, let me know in the comments what topics you want to hear about next. Your suggestions help shape future videos. Until next time, happy studying.